Welcome to our discussion today on asymptotes, vertical asymptotes, horizontal, and other kinds. Whenever you've got two expressions divided to make a function, you're probably going to find at least one asymptote. So let's talk about how to find out what these asymptotes are and if there's functions for them. So let's begin. All right, we've already figured out, or we've already talked about, either in this class or a previous class, finding the vertical asymptotes. All you have to do is set the denominator equal to 0 and solve. And remember, it's not a vertical asymptote unless only the denominator equals 0 for that value of x. If numerator and denominator are both equal to 0 for a certain value of x, that creates a hole, which is an unfancy word for what's called a discontinuity. It's like a little hole in the graph, and we've seen that before. So let's talk about how to find any other asymptotes. All right, so starting with an example, we've got 3x squared minus 7x minus 9 over x minus 1, and I want to find the asymptotes for it. Well, the vertical asymptote is easy. I set the denominator, which is x minus 1, set that equal to 0, and I get a value of x equals 1. So I know that there is going to be a vertical asymptote at x equals 1. All right, and then what we're going to do is we're going to use synthetic division to find the others. Okay, but only do this if the denominator is not a factor of the numerator. If you could factor these and cross some of the factors out, then you would definitely do that. But you can't do that in this case, so we are going to use synthetic division instead. So here we go. That's how you set it up. We're dividing by x minus 1. So we're putting a 1 out here to represent that we are dividing by x minus 1, and then make sure that all of the x's to every exponent is represented in here. I've got 3 for the x squareds, negative 7 for the x's, and negative 9 for the constant. Now if there was an x to the something missing up here, remember you've got to put a placeholder of 0 in there somewhere. All right, so remember how we do this. We leave a space, we draw a line, and we're going to copy the 3. I put a little arrow to say that I'm going to copy that 3. And then 3 times 1 is 3. I'm going to put that under the negative 7. I'm going to add these two numbers together to get negative 4. Multiply that negative 4 by the 1 that's out here, and I get negative 4. And add negative 9 and negative 4 is negative 13. So there's my answer, so to speak. But what does it mean? Well, this last number here represents my constant, or my remainder. So I put a little r there. Then working to the left, my last number is always the remainder, and the one to the left of that is always my constant. Then I've got my x's, and if I had more numbers, those would be my x squareds and my x cubes. So what I have here is 3x minus 4 with a remainder of negative 13, and that's how I write it. 3x minus 4, and I put my remainder over what I was dividing by to begin with, which was x minus 1. So that's my answer. So what I'm looking at is what happens as x approaches infinity. And what happens is that gets really big, that stays at 4, but this fraction at the very end goes off to 0 because I've got an x in the denominator, and that makes this fraction here approach 0 as x approaches infinity. So as I approach infinity, this function looks a lot like 3x minus 4, and it gets closer and closer to that function because this remainder gets smaller and smaller. So since that is the equation of a slanted line, I would say that this is a slant asymptote. So let's have a look at what that looks like. Here is the function as I would graph it. This dotted line right here, this gray one, is going to be my vertical asymptote of x equals 1, and then this blue line right here is going to be my slant asymptote of y equals 3x minus 4. So that's what that looks like with all the asymptotes drawn in. Okay, this one's worse, but that's okay. We know how to handle this. Looking for the asymptotes here. Again, I start with the easy ones, the vertical asymptote. Okay, obviously when x plus 1 is equal to 0, x is negative 1. Okay, and I plug -1 in here just to make sure that the numerator isn't also 0. And it's not. Just plug it in really quick and you'll see that the numerator isn't also 0. So that is in fact an asymptote and not a discontinuity or a hole. So let's do the synthetic division. I guess that's on this page right here. Okay, remember how to set it up. I'm dividing by x plus 1, so I will put a -1 out here. And then I've got coefficients of 1, 5, 6, and -9, so that's what I write here. Leave a space, draw a line, and I'm going to copy the 1, multiply the 1 by -1, and I get -1. Add the 5 and the -1, I get 4. 4 times -1 is -4. Add the 6 and the -4, I get 2. 2 times -1 is -2. And then add these together and I get -11. And just remembering from the previous example, the very last number is always my remainder. So I put an R there. Then working to the left, this is my constant. These are my x's. These are my x squareds. And if I had more numbers to the left, those would be my x cubes, x to the 4th, and whatever. Okay, so my answer when I divide is x squared plus 4x plus 2 minus 11 over what I was dividing by, which is x plus 1. So that's what it's going to look like. X squared plus 4x plus 2 plus -11 over x plus 1. All right, so what does that look like? Well, as x approaches infinity, then this remainder is going to get smaller and smaller so that this function looks a lot like x squared plus 4x plus 2. That's a parabola. You can tell by the x squared. So what I've actually got is a parabolic asymptote. So let's look at what that looks like. Here's the graph right here with the asymptotes drawn in. And this right here is my parabolic asymptote of y equals x squared plus 4x plus 2. And then this right here is my vertical asymptote of y. Oh, that's not right. That is my vertical asymptote of x equals -1. And I hate to end a video on a mistake like that, but sometimes that's what happens. So again, email me your questions, and we'll talk about those more in class. And I'll see you tomorrow.